Hello, we're going to talk today about complex numbers, and this is for the advanced functions course. So where are complex numbers used? Well, they're used in physics, chemistry, biology, economics, and especially in electromagnetics, computer engineering. A lot of things about your cell phone and your computer, your laptop, your iPad, your iTouch, all use some semblance of complex numbers. In fact, we're becoming increasingly dependent on them. Obviously, fields of mathematics use them, and statistics are getting some use out of it as well. Well, let's summarize some of the big sets of numbers, and let's go through them. These are numbers that we normally deal with. I think the set that comes to us most naturally are appropriately named as the natural numbers, and that's given the symbol n. Okay, so that's the set of natural numbers, and that's a set of numbers which we deal with, and these are also known as the counting numbers, also called the positive integers. And of course, there is a set of integers. Now, the set of integers is basically all whole numbers, meaning the positive, negative, and zero numbers. So, rational numbers. I didn't find a funny symbol for q, so I'm just using the letter q for this, and a rational number consists of any integer divided by another integer, and fewer numbers belong to this set than you think. Actually, the rest are actually called irrational numbers, and I'm giving that the symbol q prime, or q with a tick after it. That's like saying irrational numbers are not rational, as one would think commonsensically just by the sound of the words. An irrational number really is a number which cannot be expressed as a fraction, such as the square root of 2. And numbers like that. They're just irrational numbers. Then there's the algebraic numbers, which really can be any member of the first four sets. And they are solutions to polynomials with integer coefficients. And it's a very, very strange definition. But when we start factoring polynomials, you can keep in mind that every number we get, it will be an algebraic number. But you wouldn't believe it, but there are numbers that do not belong to this set, but are still real numbers, and they're called the transcendental numbers. And I'm just symbolizing that as not a, or a prime. That's what that tick is after it. Just like the q with a tick after it was irrational, not belonging to the rational numbers, the transcendental numbers do not belong to the algebraic numbers. So transcendental numbers are numbers which are not solutions to polynomials with integer coefficients. And examples, very famous examples, are Euler's constant, pi, and things like the golden ratio and numbers like that. And apparently there are more of these non-repeating decimal numbers than there are of algebraic numbers. So the first 6 sets of numbers are, for one thing, subsets of the set of real numbers. Okay, and that's symbolized with a stylized sort of R. Sometimes it's written as a cursive R. I found a symbol that sort of mimics what I write on the board, so I went with that. This includes all numbers on the number line. All numbers on the number line. And we mean if you pick any two numbers on the number line, and they're not equal, so long as they're not equal, you can find a number in between those two numbers, and it doesn't matter how close together you pick those two numbers. But it gets worse than that, or maybe better depending on your vantage point, that really between any two of those numbers, no matter how close you make those numbers without being equal, you can find infinitely many real numbers on the number line between any two numbers you choose, no matter how close. That doesn't leave much left over. So one might ask, well, okay, we have the real numbers, and it would be imagined that it seems that they're just all numbers that are conceivable. Well, there are some numbers that are left, I'm afraid. The inconceivable numbers, but they're not known as inconceivable numbers, they're known as the imaginary numbers. So ultimately, just to recap the past 6 sets that we've seen, really those 6 sets boil down to rational and irrational numbers, and that makes up the entire set of real numbers. Okay, they're either rational or irrational. You can go back over this video and see for yourself that, like the integers, the natural numbers, and the rational numbers themselves can all be expressed as a fraction of x over y, where x and y are both integers. Right? They all can. They all can be expressed that way. Like a whole number like 7 can be expressed as 7 divided by 1, 7 over 1. Well, that's a rational number. Okay, so that's kind of where we're going with that. All the others that cannot be expressed that way are called irrational. That really accounts for every number on the real number line. Every number in the set of real numbers is either rational or irrational. So you can actually boil it down to that. The only problem is, what's left. So one kind of complex number is simply the square root, or an even numbered root of any negative number. A cube root won't work because you will get a real number back out. So it doesn't quite work. But if you take a square root, a fourth root, a sixth root, you will get a number that is complex if there is a negative number under the surd. So these are called imaginary numbers. Now, in fact, they are a particular kind of imaginary number called pure imaginary numbers. A pure imaginary number is when you take a square root of a negative number and that's all you do, or maybe you multiply that number by a real number. Okay, so you can do either one. You can take the square root of a negative number, you can take that result and multiply it by a real number. Both are pure imaginary numbers. And yes, I did say real number. A over here is allowed to be any real number at all, like 5, 6, negative 12, and so long as we multiply by the square root of minus 1, the result of that calculation will be imaginary. So rather than writing the square root of negative 1 all the time, we can just use the letter I. Now, if you're in electrical engineering, that letter I will actually be confused with the measurement for current, and you're probably going to have to use J for the imaginary number. But being in math, we're not too worried about electrical engineering. We're going to use I for our complex numbers, like most other people do in math. So numbers of the form AI plus B, where A and B are real numbers, are called complex numbers. Okay, they're called complex numbers. So AI is called the imaginary part, and B is called the real part. So this AI plus B is pretty important. Okay, this AI plus B, A is a real number, B is a real number, I is the square root of minus 1, and we're saying that when you add these two terms together, you get a number that is complex. Okay, and that complex number has two pieces to it, one called the imaginary part, the other called the real part. Those of you who are moving on to calculus and vectors, you can actually take AI plus B and treat it as a vector. And we won't be doing that in calculus and vectors. We won't be doing that to complex numbers. We'll be doing it to other things. But keep that in mind for university in case that ever comes up. The algebra of the complex numbers. Now, the algebra of the complex numbers in some ways is very similar to the algebra you're used to, but in some ways you have to be careful. So complex numbers are added by like terms. So let's say we got 3i plus 2 and we add 7i minus 5. So we add two complex numbers together. And the way we do that is we do 3i plus 7i and we make 10i. Right? We're adding like terms. And then 2 plus negative 5 make negative 3. So we get 10i minus 3 as the result. We're adding like terms together. And so if we add two complex numbers together, the result is a complex number. Secondly, 2i minus 3 minus 6i minus 7 equals, well, how do we get this one? Well, we can just blow away the brackets and see what happens. So blowing away the brackets, we simply get 2i minus 3, which is what we started with. But notice there's a double negative here. We got minus negative 6i minus 7. So minus negative 6i becomes positive 6i. The minus sign in front also affects the 7, turning the minus 7 into a plus 7. It's just like we're multiplying by minus 1 outside the bracket. And what have we got? Well, we've got 2i plus 6i. Remember, we're adding like terms. And we make 8i. We also have negative 3 plus 7. Well, negative 3 plus 7 is 4. We end up with 8i plus 4, yet another complex number. So adding two complex numbers results in a complex number. Also, make sure you add like terms together. Just like in algebra, the I, even though the I is a quantity that is known, you still treat it like it's x or some variable. Although you have to keep it in the back of your mind, it's not a variable because it does have a definite value. Now, of course, the one case that I can think of when you get a real number is when you subtract an imaginary number from itself. So you get a real number that way. Imaginary numbers, when multiplied, also have certain subtleties to them. And I'm going to stick to I for this one because you want to watch the subtlety here very closely because this is an important subtlety. If we have I, we have the square root of minus 1. If we have I squared, it's like the square root of minus 1 squared. Well, that's just minus 1. Notice that by squaring I, we actually get a real number. Important to know. So now if we multiply by I again, we get I cubed. Well, that's like negative 1 times the square root of minus 1, which is this. And that's negative the square root of negative 1. There's a negative sign both inside and outside the surd, and they do not cancel. Finally, I to the fourth. Well, the easiest way I can think of solving this one is to think of I squared. Well, we know what I squared is. It's negative 1. And if we square I squared, we get I to the fourth. So we can use negative 1 squared. Negative 1 squared is positive 1, another real number, and this time a positive real number. And you will find that if you find I to the 133rd, I to the 128th, I to the 1521, whatever you like, you will always get numbers that are one of these four, no matter what the exponent is on I. Okay, will always be one of these four. So raising I to successive integer powers like I to the 5th, I to the 6th, I to the 7th will actually cycle through these same four results over and over and over. Multiplication of complex numbers. Well, for multiplication, you can use FOIL. Remember, I is kind of like x, except we know the value. It's not really x because it's not a variable. It actually is a constant. We can't add real to imaginary either. Like 3 plus I has to stay the way it is. We can't just make one number out of it. Well, technically they are one number, but we leave it expressed as 3 plus I. We can't really mix them. So, however, you can multiply real and imaginary numbers. So like, let's say that we have, this is a very general treatment here. Let's say A, B, C, and D are any real numbers. Okay, so we have AI plus B times CI plus D. AI times CI is ACI squared. And then AI times D, ADI, and B times CI is BCI, that's over here, and B times D is BD. So that's what we have. Now notice some things. ACI squared can be expressed differently because I squared, remember, is equal to negative 1. So really, what you're looking at here is negative ACI. And also, you can notice also that negative AC as a result of ACI squared becomes a real number now. And BD is also a real number. We have actually now two real numbers in this expression and two imaginary numbers, ADI and BCI. Well, we can group together like terms, BD, which is real, and AC, negative AC that is, which is real, to make BD minus AC. Plus, you factor I outside of ADI plus BCI, you get I outside of AD plus BC. So what you have here really, BD minus AC is just an imaginary, not an imaginary number, it's just a real number, and I times AD minus BC is just a pure imaginary number. So once again, if you multiply two complex numbers, in most cases, the result will also be complex. And if we're letting A, B, C, and D be any real number. And this works best if A, B, C, and D are not equal to each other. So let's try the following. Let's try messing this up a bit. Let's find out what happens when they are the same. So let's say we have I plus 1 times I plus 1. We're squaring a complex number. What happens? Does it blow up? What does it do? So here we have I times I, which is minus 1. And then the rest is just 1 times I plus 1 times I. That's just I plus I. And we get plus 1. Well, any guesses as to what's the result? Well, the result is 2i. And so that teaches us that squaring a complex number yields a pure imaginary number. Try this yourself. I'll give you a minute. In fact, you can just stop the video for a few minutes. Okay, so the result of this is 2i times 9i is 18i squared, or negative 18. That's what this is. And then we do the rest of the FOIL method. 2i times negative 4 is negative 8i. 7 times 9i is 63i. And then 7 times negative 4 is negative 28. And just do the last step, clean it up. I'll give you a few seconds. Okay, that's 55i minus 46, if I'm not mistaken. I think I did that math mostly in my head, but I believe 55i minus 46. Yeah, that's right. Okay, let's try this one. So as you can see, when you multiply two unlike complex numbers together, the result will be complex. What about this one? This one's kind of peculiar. 3i plus 4 times 3i minus 4. And look at the sign in the middle. The sign in the middle is the only thing that's changed. This is what's called multiplying by the conjugate. But you know what? The rules are the same. Try it yourself. Why don't you just pause the video and work it out yourself, and I'll come back on. Okay, so we get 3i times 3i, which is negative 9, and then negative 4 times 3i, which is negative 12i, and positive 4 times 3i, which is positive 12i, and then 4 times negative 4 is negative 16. Notice we have plus 12i and minus 12i. When you subtract them, they go to 0, and all you get is negative 9 and minus 16, which is negative 25. So negative 25, well, that's a real number. Multiplying a complex number by its conjugate yields a real number. In fact, that's quite that's actually how to get a real number. So you might want to remember that if you ever have to deal with real numbers in the future. So what does this mean? When you use the quadratic formula, and we're talking about what this means for like broader mathematical concepts. Let's say you use the quadratic formula, you search for x-intercepts for parabolas, you'll always get two roots. And even though you get maybe the square root of a negative number underneath a radical or something like that, and then your teacher says, no, that number's no good, you don't use it. And of course you don't use it, especially if you're graphing. If you're putting stuff on a graph, you're not going to use it. But does it mean that there's no root? No. What it means is there's no real root. However, there are complex roots. So if you got two complex numbers in factoring a parabola or factoring a quadratic, then what that tells you is that there are two complex roots. And of course, you can't plot them. There's no way to do that because you've got a Cartesian plane. You don't have a real and imaginary plane. That's a different plane. It's called a complex plane that you'd have to plot that on. The guarantee that that a quadratic, which is otherwise known as an order 2 polynomial that will yield exactly two roots, is guaranteed by the fundamental theorem of algebra. The fundamental theorem of algebra states that for any polynomial of order n, that means the highest exponent on the polynomial has to be some n value. Let's say it's 6. Okay, so let's say there's an order 6 polynomial, that they will always have 6 roots. Now there might be double roots somewhere. That may be true, but let's say it's quite possible that an order 6 polynomial may not even cross the x-axis anywhere. If you had to plot that thing, it probably will never touch the x-axis ever, anywhere. And if that's the case, then what you have to say now is that you have 6 imaginary roots. The fundamental theorem of algebra says that if you have an order 6 polynomial, that there will be 6 imaginary roots. An order 5 polynomial, not 6 imaginary roots, but 6 roots. It'll be 6 roots. Some of them will be complex, some of them will be real. But in the case of the order 6 polynomial that doesn't cross at all through the x-axis, then all 6 of them will be complex. And you have also, like for example, a quadratic. If a quadratic never crosses the x-axis, then both roots are what we call complex. And thanks for viewing my program.